Previously, we talked about DRAM. And at the end of last semester, we talked about 3 different organizations of a memory controller and the DRAM chips. Either you have a independent single memory controller, which can manage one DIMM in one DRAM channel. You have a command bus and then a data bus. Because data bus is always the bottleneck. The memory controller tend to read some consecutive data. So maybe one command will trigger 8 consecutive bursts like this. Sometimes if you have 2 DIMM, they can share the same channel, the same memory controller. But again, each DIMM is one channel. So 2 channels share one memory controller. And eventually, if you have some high-end, really high-end CPU, then the CPU will allocate a single memory controller to each DRAM channel. When you have multiple channels, multiple DIMMs, multiple banks, multiple ranks, each rank is the DIMM share one command bus. So you have a lot of units to management to do the management, and you need to maximize the parallelism among these units. And you also need to consider the row buffer hit rate. And that's the reason why we have a different mappings like this. Assume you have one array. Array A from element 0 to element, let's say, n. Totally, you have n+1 elements. Each element costs 4 bytes. So when we increase 1 here, this is a 4 byte offset. Address 0, address 4, 8, 12. Of course, this is in hex format. So each element, for example, the A0 4 byte, I can put A array like this. This is A0, A1, A2, A3, A4, A5. In this layout, or I can put A like A0, A1, A2, A3 in this layout. Which layout is better? Which mapping is better? This is totally decided by your application behaviors. If your application always try to sequentially read the data, maybe the first one is better because I'm sorry, if you application sequentially read the data, maybe the second one is better because here at the same time you can read multiple elements. So at one time you can read this one, this one, this one, and this one, because these 4 banks can be independently accessed. If your application does not sequentially read the data, then maybe you prefer the first one. So each time you just access one bank. And then maybe next time, if you read, let's say the element 9, you can access this bank. Then the first request and the second request has no conflict. And the mapping is also related to the open page policy and close page policy. So let me first introduce what's the open page policy and closed page policy. So this is your bank. This is your row, one row, and this is your San file, and this is your row buffer. During one read operation, you read the data from the row to the San file. Like this. And then you write everything into the row buffer. This means you open a row. So when the row is open, when you have this scenario, you have two different options. The option 1, you can keep this row open and just wait and do nothing. So if your application has a consecutive read to this row, then you don't need to open the row again. You can directly send the data out of the row buffer. I believe we have this example. So here, yeah, like this here. After you open a row, you only need to send the column address. You don't need to send a row address anymore. You just send the column address, which select only a portion of the data from the row. And then the row buffer will pump out the data you want to have. This is good for the application who will heavily access the same row. But if your application want to access another row, let's say this row, then you have to close this row first. And the row closing latency will be added to your memory access latency for the second request to a different row. If you know that my following request will not access the same row, then after the first request, you can actively close this row. Close row means you write the data back to this row, do a restore on this row. And then you have an empty row buffer, you have an empty San file. Then when the next request come to the bank, you can directly read the data from the second row. You don't have to close the row anymore. This is so-called closed row policy. Because the opening latency and the closing latency of the row is very long. So this policy may have a huge impact on the application performance. Again, this is related to your application behavior, whether you have a consecutive request or not. If you have a random request, of course, you will definitely prefer the closed row policy because you have no heat in the row buffer anymore. But if you have a very regular, very consecutive access pattern, then you prefer the open row policy. So this is the overview of your CPU, the memory, the DRAM. You have a CPU here. This is your CPU. You always see when you buy a CPU, when you buy Intel AMD CPU, they talk about front side bus frequency. And maybe 1G or 2G or 4G. This frequency of this bus significantly decide the performance of your entire computer. Why? Because the bus is used to connect your CPU to the NOS bridge. The NOS bridge is actually your memory controller. And your memory controller can talk to the DRAM. It can also talk to the GPU, because the GPU is also another high performance equipment. And you have a cheap source bridge. The source bridge is I cannot say it's a part of memory controller, but it's a slavery of the memory controller. The memory controller can manage this source bridge. The source bridge is very cheap, and it also very slow. It only talk to very slow devices like your flash drive, your disk. So this is the reason why the frequency of this bus, NOS bridge, the bus front side bus is very important, which has a huge impact on the performance. And this is some low-end CPU. They have a separate memory controller and the CPU, and they use a bus to connect them. For some high-performance CPU, okay, this is the motherboard of the the separated design. You have a NOS bridge, you have a CPU, you have a source bridge. You can see that the CPU is very close to the NOS bridge, so that you have very short bus, and the bus can easily achieve higher frequency. Also, the DRAM is very close to the memory controller compared to the source bridge here. See, your source bridge is close to what? Close to the USB drive, the disk. So for some other high-end CPU, you have very large CPU here, and the memory controller is integrated to the CPU. Then you do not have so-called front side bus anymore. The bus is integrated in the CPU itself, so you can see that it's easier to achieve higher frequency. And then the memory controller integrated in the CPU can talk to the memory here. And you also have source bridge. So the structure in the memory controller is very simple. You just have a read queue, write queue, and this is the response queue. Response queue is used to store the reading data. You send a request and address here, and I return the data to this response queue. You know, the CPU may be busy with some other things. I just prepare the data ready in this response queue. When the CPU is idle, it can fetch the data it needs from this response queue. And this scheduler can do some lightweight scheduling. It can give higher priority to some requests. For example, those requests go to idle banks. So if you require, if 80% requests go to a very busy bank, and 20% will go to some idle bank, that 20% may go first, because those banks are ready to use. And you also have some buffers to temporarily buffer the data. In this example, we have 2 channels. So memory controllers start to work after you have a cache miss. And it needed to manage, of course, the read and write operation to the DRAM. It also needed to manage the DRAM refresh. Open row, close row policy, mapping. When you change in some high-end servers, you can actually change those mappings in your BIOS system. After you change the BIOS system on this address mapping part, the memory controller will also change it inside. It's inside logic. And it can also do some scheduling between different banks, between different channels, between different ranks. So you can see that the memory controller is actually a very important component, especially nowadays. Every application will read a lot of data. Again, this is open page policy and closed page policy. It also have a different scheduling policy, which is a so-called first come, first serve. This is a very easy one. And another one is a first ready, first come, first serve. Upon this first come, first serve policy, the memory controller needed to check whether this rank is ready to use or not, whether it's busy, this bank is busy or not. It needed to maintain a table to record the working idleness of each bank. When it collected these information, it can do the scheduling on the DRAM command bus. Sometimes the memory controller will also give higher priority for the request who will have a row buffer hit. Now in one bank, the row buffer has been, one row has been opened. For example, this is my row buffer and this is my row. This row has been read into the row buffer, has been written to the row buffer. Then the memory controller will schedule the request which will go to the same row, like this row buffer first, so that you have more row buffer hit. It will reorder the request so that more requests go to the same row will go first. So in this way, it can increase the row buffer hit rate. And of course, reduce the average request serving latency. If there's no row buffer hit rate, then it go back to the first come, first ready, first serve policy. Actually, scheduling those requests is very difficult. Why? Because you have a lot of timing constraint. Now you have a DDR2, DDR, DDR2, DDR3, DDR4. Now, very soon you will have a DDR5. These DDR standard will have a different timing constraints. For example, only after maybe 5 cycles, you can issue a column address. After you issue the column address, after maybe another 8 cycles, you will receive the first piece of your data on the data bus. So you have all these 8 cycles, 5 cycles timing constraint. Then your memory controller need to understand all these constraints so that it can receive and send the request in the right timing. So this is the reason why if you have some old computer which can only support DDR3, then the computer cannot use DDR4 DRAM chips. So, they have different timing. And the aim of the memory controller, of course, is to maximize the throughput of your DRAM system and to minimize the latency of your DRAM system. Now your CPU becomes faster and faster, but the DRAM actually becomes slower and slower. Why? Because your DRAM system becomes larger. You have a larger capacity, now 16 gigabyte or 32 gigabyte. Originally, it's only 1 gigabyte. with a larger capacity, your DRAM system actually becomes slightly slower than before. So what if your memory latency is a 10K cycles? Then you need to explore so-called memory levels parallelism. The memory level parallelism can be enforced by having multiple banks, because now you can use multiple banks. You can issue the request to different banks and have the data concurrently. Then they try to modify the memory controller, modify the structure of your DRAM to improve this so-called memory level parallelism. So this is one example. We have a fixed miss rate for the cache. What if we have a 1.5 memory level parallelism, which means that each time we can serve 1.5 requests on average? Then this is your memory access average latency. If you can improve this metric, then this is your neural latency. You can see that by improving this memory level parallelism, we can significantly reduce the memory average access latency. Of course, we have another scheme to further reduce the memory access latency. First, you have a better cache. You have back to this example, you have a cache with a higher hit rate, means lower miss rate. When you reduce this number, the memory access latency can be also reduced. But again, cache is a very old component. People try all the schemes to improve the cache behavior. Further reduce the cache miss rate is very difficult. And then you can improve memory level parallelism. So the caching can reduce the number of your DRAM access. And the memory level parallelism can improve the concurrency of your DRAM memory access. And we can also do some prefetching. Prefetching means before you generate the need, I prepare the data ready for you, so that when you just have that miss, I can immediately give you the data you want. You don't need to wait for the DRAM access anymore. But again, somehow the prefetching do some prediction on the memory behavior. Again, it may not improve the performance for all applications. If your application has a very simple behavior, for example, consecutive read, then it's easy to do the prediction. The prefetching can work very well. Unfortunately, if you have some very random memory access, then it's impossible to do the prediction. Then the prefetching may not work at all. So this is about the DRAM. Any question? If no question, I will talk about the so-called non-runtime memory technology. Nowadays, you can see that the memory part becomes more and more important. All about the big data applications. Even your deep learning application, even if you heavily depend on the GPU, the memory is still a big bottleneck. Why? Because the ImageNet data set cost maybe 100 gigabytes. You don't want to always read those images from the disk. You want to put those images into memories so that you can have a shorter latency. Your GPUs do not have to wait. So traditionally, we just need 1 GB or 2 GB memory. Because we only run some simple software like Office. But now we have a big data applications. Again, we need to store images or even the entire database, videos, photos in the memory, and these these applications require zettabyte or even yottabyte data. It's larger than terabytes. One simple solution is, of course, we increase the memory, not only the DRAM, but maybe the cache. We hope we can have a larger cache system. Although the Moore's law is arriving its end, because now we have a 3 nanometer or 2 nanometer. At the CPU level, people still want to continue this so-called Moore's law by integrating more and more cores into a single chip. Although on your laptop, you still have 4 cores, 8 cores, because the application on your laptop has a limited parallelism. You don't need it. Or you have a fancy GPU in your laptop. That's enough. But for some high-end scientific computing, people may require 128 cores. So some HPC company, high performance computing company, will produce those CPU with many cores to support them. Then we need a large cache and a huge memory capacity to maintain a sustainable performance for those many cores here. So traditionally, this is not an issue because, larger capacity DRAM, larger cache only represent a larger chip area. We just need to integrate more and more transistors to implement that cache, to implement those DRAMs. Again, larger chip may, of course, will be more expensive because we have a lower yield and a higher fabrication cost on those larger chips. So in maybe 2000s, 2010s, this is not an issue because we can always have a more advanced technology node. We have a smaller process technology. Back to our course, we have a smaller gates. We have a smaller inverter, smaller access transistor. So in this way, we can make the chip area smaller, although we need a larger capacity DRAM or cache. Unfortunately, now we cannot make that trend anymore. Why? Because of the poor scalability of DRAM. Again, in our previous lecture, we talk about the structure of DRAM. It's simple, just a capacitor and access transistor. So if we can make everything here smaller, then the cell is scalable. But unfortunately, if we reduce the size here, reduce the size of the capacitor, it's difficult to sense the cell. Why? Because now it only have maybe several charges. If you further reduce the size, maybe sometimes you don't have one charge at all. A single charge you cannot hold. At that time, you cannot distinguish 1 and 0 anymore. And when you reduce the size of the access transistor here, the charge will leak away through this gate faster. So when you reduce this one and when you reduce this one, you don't have charge at all. The charge cannot be stored in this part at all. And you need more frequently refresh the cell, even you have some charge here. Then the power consumption will be huge. Because of these reasons, we cannot make the cell into a smaller size. Now we have 5 nanometer or 3 nanometer. The scaling of DRAM beyond 22 nanometer is becoming challenging. So nowadays it becomes more and more challenging to make the cell into a smaller size. Basically, we have the same DRAM cell size generation over generation. Now we cannot reduce the chip area anymore. Even we have a new memory, new process technology, new memory technology. In a data center, 20%, almost 20% power is consumed by the DRAM because they need a lot of DRAM. For your mobile phone, even you shut your mobile, even you keep your mobile phone in sleep mode, you still need to do the refresh in the DRAM. Otherwise, you will lose your data forever. Next time when you try to power up your mobile phone, try to wake up your mobile phone, you will suffer from a very long latency. That will hurt the user experience a lot. And nobody wants to build this for the data center. And actually nowadays, people did this, bring a multiple copy of battery to support only one smartphone. Here shows the comparison between them, the scaling of the core. This is the core number. And this is the memory capacity per core. Although overall, the DRAM capacity increases year after year. If we use the capacity of DRAM divided by the core number, then this is the result. The result may not be increasing every year. So sometimes you even have a decreasing here. Then we need to look some alternative technology to the DRAM. Here, I list a table to compare the potential memory technology to replace DRAM. We have a DRAM here. This is read latency, write latency, power consumption, cell size. F here indicate the feature size. If you use 22 nanometer to fabricate the cell, then this is 22. If you use 5 nanometer to do the fabrication, this is 5. The endurance means after you write a lot in one DRAM cell, the cell eventually will be broken. Although for DRAM, this number is very large. No one actually have a lot of die cells because of frequently write. You do have die cells in the DRAM. If you have die cells, how the chip can handle this? The answer is ECC. So they will treat this error, the die cell, as a error. Then by the ECC, you can still correct this error. Because you barely have one in a chip, then the ECC overhead is not very large. So DRAM is used to implement the memory system. I also list the SRAM. We talked about SRAM before, which is an on-chip memory technology. It's very fast, but very power hungry. And you can see that by 6 transistor, this is our cell size. And it is used in the cache. And we also have SSD flash. And you can see this is the latency, how slow they are. And this is the cell size. The good news is it's very dense. The cell is very small. You can easily have maybe 8 terabytes nowadays. But it's very vulnerable. You can only write maybe 10K times, and then the cell will be dead. So this is the SSD. So in this lecture, I would like to introduce some other memory technology, like the phase change memory. It's a new type memory technology. It has very small cell size, longer than flash endurance, better than flash reliability. The read latency can be comparable to the DRAM, but the write latency is much longer than DRAM, but it's still faster, much faster than the flash. More advanced technology is the STT-RAM and RRAM. They have very fast latency, longer endurance compared to PCM, and different cell sizes. They can be used to implement the future cache and some compute logic. So in this lecture, I would like to focus on the phase change memory, particularly the comparison between the phase change memory and the DRAM. I think the major advantage of the phase change memory is the cell size. The cell size is very small compared to DRAM. It uses a totally different mechanism to store the data. So there's no charge, no leakage. You don't need to refresh the cell at all. So this is good news. The bad news is that the write latency is super long compared to DRAM. And you also need to take care of the endurance. After a certain number of writes, the cell will be broken. And the write power is larger than the DRAM. So when you just see this, when you just look at this table, it's really difficult to say whether DRAM is better or the PCM is better. But for the current big data application, those applications has much more reads than writes. Then consider the read latency of a PCM is very promising. Then big data application can actually benefit from it. So now you can buy the related product of this type of memory on the market. But again, it's more expensive than the DRAM. It's used in some server level CPU. So traditionally, we have a multi-core here, a small SRAM cache, a moderate capacity, maybe 32 gigabyte DRAM for one single PC, for one single server. Future, we may have some STT-MRAM integrated on chip, and a normal DRAM, small capacity DRAM to serve as a cache. And then we have a huge capacity of a PCM, maybe several terabytes PCM as the main memory. So first, I would like to present some background on the phase-change memory. Phase-change memory uses so-called materials, phase-change material, to record the data. And this is the material. The material is actually some chemical compound like this. The material can be in two states. The first one is a so-called amorphous state. It has high resistance. The second one, the other one is a crystalline state. It has low resistance. By the application of heat, we can switch between these two states. By high resistance and low resistance, we can, store 1 and 0. Then the array structure is similar to DRAM and SRAM, but you just need to replace the capacitor by the phase memory cell like this. And you also need a access transistor here to select that row. In the middle of the cell, there is a layer of so-called phase-change material. And this is a heater, very small heater. When you apply a very long duration, but a small amplitude current, we can program the cell into the crystalline state. By a very short duration, but a large amplitude current, we can program cell in amorphous state. Not all the material in amorphous state, but maybe only the portion close to the heater to the amorphous state. And then the resistance will change here in this layer. So in this way, you can change the data in the PCM. The lowest resistance is 1K ohm. Highest resistance is 100 million ohm. There is a huge difference between these two. Unlike the DRAM, the sense amplifier needed to, in the DRAM, the sense amplifier needed to detect the difference between several charges. But for the PCM, it's very easy for the sense amplifier to sense the difference between, the large resistance difference. So it's possible to integrate more states in the middle of this range. So here you maybe have a 1K ohm, 100K ohm. Here you may have a 10 mega ohm. Then in this way, you can store 2 bits. This is so-called a multiple level cell. By multiple level cell, of course, without any extra overhead, you can double the capacity and reduce the cost per bit. But you also need to add the read-write latency, write power, and you need to more frequently write the cell. And then the endurance will be shorter. Any question on the new type of memory? So if no question, we will continue to introduce the PCM next lecture. And then we can stop today. Thank you very much.